We have now provided ourselves with two basic approaches for trajectory optimization. In the first, we are optimizing over some fixed number of variables using the methods of nonlinear programming. And in the second, we are trying to optimize over the entire trajectory, in essence, optimizing an infinite number of variables via the methods of optimal control. These two approaches are not unrelated. What we find, and what is described in that 1998 Betts survey paper, as well as many other works, is that as the number of variables that we are optimizing over in the nonlinear programming problem grows, the solutions begin to approach the solutions that we get from optimal control. In essence, the necessary conditions for optimality for each of the two approaches start to look the same as the number of variables increases in the nonlinear programming problem. The Lagrange multipliers that we use in the nonlinear programming problem can be interpreted as discrete optimizations of the optimal control adjoint variables. Regardless of what approach you end up taking for your trajectory optimization, you will need to employ iterative numerical methods in order to get to your solution. And a particularly important set of methods are known as shooting methods. Shooting methods allow us to solve boundary value problems by turning them into initial value problems. Our basic setup is that we have a boundary value problem given by a differential equation x double dot is equal to f of x, x dot, and t. We have some initial conditions x naught at time t naught, and we have some desired final conditions xf at time tf. We can write a corresponding initial value problem that has the exact same dynamics and the same initial condition in the state, as well as an additional initial condition in the state derivative, x dot naught, and a solution, x, as a function of x dot naught and time. We define a function g of x dot naught that is equal to this solution minus the final state. If this function has a root of x dot naught, that is, if g evaluated at x dot naught is equal to 0, then the solution, x of x dot naught in time, is a solution of the original boundary value problem. The upshot of this is that we have turned the problem of searching for a solution to a constrained differential system to one of root finding. We effectively have to find the roots of this equation g, and that will give us exactly the solution that we wanted in the first place. And we have lots and lots of ways to do root finding. We can further split shooting methods into two different categories: direct shooting and indirect shooting. In direct shooting, we are going to assume a functional form for our control input. That is, u of t is equal to the sum over m functions phi I, that are functions of time, where these are known functions, each multiplied by some unknown parameters g sub I. We will set up nonlinear programming problems to solve for the g sub i's such that whatever our cost function j is for our given system is minimized. So direct shooting maps to that first category of methods that we have for trajectory optimization, the nonlinear programming methods. In contrast, when we do indirect shooting, we assume some initial or final values for our state and co-state elements, and then we numerically integrate the Euler-Lagrange optimal control equations either forward or backward in time, and attempt to minimize the difference between the states that we get on the other end and their desired values. So indirect shooting methods are the optimal control methods. So between these, we've covered pretty much the full space of what is possible in terms of optimizing our trajectory systems. These specific approaches are almost countless and hugely varied. The body of literature is immense, and we have just barely scratched the surface of it, but we have provided ourselves with a basic description of what is out there. And what you have to keep in mind is that your final trajectory will be the result of detailed numerical optimization using at least one of these two approaches and possibly both. What we're going to turn to now are applications of these methods, and we're going to look at first the setup for fuel and energy optimal trajectories, and then finally close with some worked examples from a variety of papers. In order to talk about fuel optimal trajectories, we first have to quickly remind ourselves about rocket propulsion. Rockets are reaction thrust systems, which means that they throw out mass in order to produce thrust. We can quantify the relationship between the mass flow and the thrust in a couple of different ways, but most commonly, we define an effective exhaust velocity as the ratio of the thrust force generated to the mass flow rate, m dot. In the case of a conventional chemical rocket system with a combustion chamber and then a converging diverging nozzle, we can write this effective exhaust velocity as the exit velocity of the fuel from out nozzle plus the nozzle exit area scaled by the mass flow rate times the difference between the exit pressure at the nozzle outlet minus the ambient pressure. If we assume no other forces acting on our rocket other than this thrust force, and that this effective exhaust velocity is constant, we can solve for the delta V generated by the thrust as the integral of the specific force, that thrust force divided by the rocket mass, from a time t naught to a time tf, where this is the full time of your burn. We can rewrite this as the integral of the mass flow rate divided by the mass, all scaled by this effective exhaust velocity, where we're just substituting in this definition into this integral. This term is dm dt, and so the dt's cancel, and this all becomes negative the effective exhaust velocity times the integral of 1 over the mass from some initial mass to some final mass. And this is all solved as delta V is equal to the effective exhaust velocity of our system times the natural log of the ratio of the initial mass to the final mass. And this is known as the ideal rocket equation, or the Tsiolkovsky rocket equation. You will frequently hear people talk about the tyranny of the rocket equation, and that lies in this natural log term here. This means that the delta V that you're able to produce is hugely reliant on how much of your rocket is composed of fuel mass. This m naught is your rocket payload and structural mass plus the fuel. And if you burn all of your fuel, this m final is just the structure and the payload that's left over. Because of the nature of the natural log expression, this ratio goes up very, very quickly as you're trying to produce more and more delta V. And you very quickly find yourself having to devote more than 99% of your total mass allocation to just fuel. And this is the primary reason why rockets are staged when they are departing the Earth's surface. We augment the ideal rocket equation with the definition of specific impulse. Specific impulse is defined as the ratio of the total impulse generated, that is, the integral of the thrust force over the time of thrust, to the propellant weight, which we call WP. And it's important to note that this is propellant weight, not propellant mass, and specifically the weight at Earth normal gravity, so at Earth's surface. If we assume a constant thrust and a constant mass flow rate, we can again substitute for this using our previous definitions and write the specific impulse as the thrust force scaled by the mass flow rate and the standard gravity g naught. Ft over m dot is the effective exhaust velocity, and so the specific impulse can also be written as the ratio of the effective exhaust velocity to Earth's surface gravity. With this definition, we can rewrite the ideal rocket equation as the change in velocity due to our rocket thrust is the specific impulse of the rocket times Earth's surface gravity constant times the natural log of the ratio of the initial mass to the final mass. When you work this out, you will find that specific impulse in this formulation has units of time. Typically, it's given in units of seconds. Chemical systems will typically have specific impulses of hundreds of seconds, with the most highly performant ones having somewhere on the order of 300 to 400 seconds. And they will develop thrusts of many newtons, potentially even thousands to tens of thousands of newtons for rockets intended to lift off of the surface of the Earth. Electrical propulsion systems are much, much more efficient in the specific impulse sense. They can have specific impulses of thousands to even many thousands, but they are typically much, much less performant in terms of thrust magnitude and will have thrust forces of below single Newton values. And in some cases, for specialized systems, even at the millinewton to micronewton range. These systems are typically only good for in-space propulsion and can never get you off the ground as they are currently formulated. With these basic definitions in hand, we can now formulate the fuel optimal trajectory problem. We are optimizing a state composed of our position, velocity, and spacecraft mass, which we now have to treat as a time-varying variable because we're going to be using some of it as we burn the fuel. The first derivative of our state is given by the derivative of position, which is velocity. The derivative of velocity, which is our perturbed gravitational system, in this case perturbed by a control term, by our thrust force. We will define T max as the maximum possible thrust force. U will be a thrust ratio. You can think of this as a throttle term, so it varies between 0 and 1, scaled by the current mass of our system, multiplied by a thrust direction. So our total control is dialing in U, which varies between 0 and 1, and dialing in the vector alpha, which tells us in which direction we are applying the thrust force. And finally, from the ideal rocket equation, we know that our mass is changing as the thrust force, which is the maximum thrust times our current value of U, scaled by the specific impulse and G naught of our system. We will normalize the mass units such that we start our trajectory with one mass unit. So one mass unit in this case represents however much fuel we are able to carry. And we have some known initial position and initial velocity. We also have a known desired final position and potentially a desired final velocity, but we have to leave the final mass term open. We could set this to 0, but that would require us to burn all the fuel that we carry, which is not necessarily what we want. In fact, if we are using a fuel optimal trajectory, we want to burn as little of the fuel as possible. So we leave this final mass term as an open term to be optimized. And our cost function is the integrated control over our trajectory. And because this thrust direction is assumed to be a unit vector, it's really just the value of U that controls how much fuel we've burned. In order to get it into physical units, we again scale by this maximum thrust divided by specific impulse and standard gravity. But the really important thing here is that we're integrating from T0 to TF the value of this thrust ratio term U. From this, we formulate the Euler-Lagrange equations, and our Hamiltonian is given by the costates multiplied by the dynamics plus the T max U over ISP G naught term. And the costates are defined one-to-one with our optimization state. So we have a costate lambda sub r for position, a costate lambda sub v for velocity, and a costate scalar lambda sub m for our mass term. The fuel optimal trajectory solution is given by the thrust direction being set to negative the unit vector of the velocity costate. The thrust ratio can be 0, 1, or somewhere within the range of 0 to 1. And we parameterize this choice by introducing this rho parameter, where rho is given by 1 minus the specific impulse times G naught scaled by the current mass times the norm of the velocity costate minus the mass costate. We can now evaluate the Euler-Lagrange equations, which tell us that the time derivative of the costates will be the partial in the state of the Hamiltonian, which evaluates to this matrix here. Our boundary conditions are that the position and velocity have to match and that the mass costate has to go to 0 at the final time. We turn this into a root finding problem via the shooting function and numerically iterate until we find a solution.